All right, we're going to have another look at this idea of rates of change. So all of this topic has to do with rates of change. So a reminder that our derivative basically measures a rate of change. So one quantity changing with respect to another quantity. Now, the steeper the curve, the faster that quantity is going to change. So here's a little graph. So at P, the slope is positive, so we say the graph is increasing. Now you could have one at Q, which if I draw the tangent in, it's horizontal, so the derivative would be 0. That's where the curve is stationary. And then there's something like R, where the slope is negative, and so that's where the function is decreasing. If I was to draw a secant rather than a tangent, so here's a line that's going through P and Q. So if I have a slope of a secant, that will give me the average rate of change as our point moves from P to Q. As opposed to our derivative at any point gives us the instantaneous rate of change. What's happening at that exact moment in time. So the instantaneous rate of change. Well, let's take a journey back to travel graphs. Back in the junior school, you would have seen a travel graph that maybe looks something like this. Very blocky, lots of straight lines. So we've got a coach, it's leaving the depot at 9 a.m. and it's going on a one-day tour. And you get asked questions like, oh, how long was the first stop? And how did we find the first stop? Well, we had a look for when the graph was flat. Now, at the time we didn't realise it, but what we were looking for are stationary points. When is the slope equal to 0? It's a horizontal line. Well, the first time that happens is over there at 10:30, I think it is, and it goes for 30 minutes. When did the coach start to return to the depot? So we're now decreasing our distance from the depot because we're coming home. So the graph is going down, and that is at 1:30 p.m. How fast was the coach travelling on that return trip? Well, remember, speed equals distance over time, and we're travelling 200 kilometres in 2 hours, so 100 kilometres per hour. It would actually be the slope of that downwards line. And the average speed for the whole trip? Well, over the whole trip, we travelled 400 kilometres and 6.5 hours from when we left to when we got back. So about 61.5 kilometres per hour. Of course, now that we know calculus, we don't have to have those blocky graphs. We could have something like this, where a ball is bounced and its distance from the ground is graphed. So as it goes up, the distance is getting further and further away, so it's increasing. It'll stop and then come back down. Now we could actually work out an equation for this. It turns out to be a parabola, and it's 5t outside of 8 minus t. The distance, remember, is the total amount travelled. We now have another expression called displacement. Displacement is how far are we from our reference point, usually the starting point. Find the height of the ball after 1 second. Well, we could read off our graph or plug it into the equation. T equals 1, we get 35. So 35 metres above the ground. At what other time is the ball the same height? Again, we could read off our graph, or we can use our equation. When is x equal to 35? So 5t outside of 8 minus t is 35. We end up with a quadratic. We get two possibilities. T equals 1 or t equals 7. Well, we know the first time was at 1, so the other time must be 7 seconds. Average velocity. So that's the secant. Change in displacement over change in time. Just like the slope formula, x2 minus x1 over t2 minus t1. Find the average velocity during the first second. After 1 second, it was 35 metres above the ground, and it started at 0. So we end up with 35 metres per second. What about the 5th second? So going from t equals 4, and we can calculate that, it's 80, to t equals 5, 75. But again, average velocity. Just like the slope formula, we get -5. So during the 5th second, it was -5 metres per second. Well, what's the significance of the negative? Well, that tells us we are decreasing, so we're coming back down. Find the average velocity during the whole 8 seconds. Well, we started at 0 and we finished at 0. So weirdly, the average velocity is 0 metres per second. And to make some sense out of that, If I only looked at it at t equals 0, I'd say, oh, there it is on the ground. If I went away and did something and came back 8 seconds later, I'd go, oh, it's still on the ground. So its velocity is 0. It didn't move as far as I'm concerned. Average speed is when we use distance instead of displacement. So the average speed for our journey, well, it went up 35, but then it came down 35. So it travelled 160 all up. Divide that by 8, and we actually get 20 metres per second for an average speed. Okay, so 9a, let's play around with our travel graphs.